In this video, we're going to do a comparison of cylindrical and spherical coordinates by parameterizing the same surface both ways. So here what I want us to do is parameterize the portion of the plane z equals 4 that lies inside the cylinder x squared plus y squared equals 4. First of all, we're going to do it using cylindrical coordinates, and then we're going to do it using spherical coordinates. So first of all, let's make sure we understand the region. The region is going to be a part of the plane. So here, this is going to be this blue disk, which is inside the cylinder, x squared plus y squared equals 4. So the cylinder, in a certain sense, is giving us the bounds on the region. But remember, what we're parameterizing is the plane. So we're parameterizing something that has equation z equals 4. Now we're going to do this first using cylindrical coordinates, which are x is r cosine theta, y is r sine theta, and z equals z. And then we're going to come back and do it using spherical. One extra step that I want us to do this time, though, is after parameterizing it, I want us to figure out what the bounds on the parameters need to be so that we get exactly this disk. That way we would know what the bounds would be if we were going to carry out an integral on the disk, for example. So first of all, let's use cylindrical coordinates. So, in our thought bubble, we're going to think general cylindrical coordinates. X equals r cosine theta, y equals r sine theta, and z equals z. And we're going to substitute those into the equation for the plane. Well, ta-da, z equals 4. So I take that z equals 4, substitute it in over here, and I get the parameterization x equals r cosine theta, y equals r sine theta, and z equals 4. And that's my parameterization. Phi of r and theta is r cosine theta, r sine theta, and 4. I keep saying this, but notice that when I parameterize the surface, I should have exactly 2 parameters. So there are only 2 variables here. Now let's see what the bounds on this are going to be. To work on the bounds, let's figure out what the equation for the cylinder is in cylindrical coordinates. Well, we know that the cylindrical coordinates x squared plus y squared is the same as r squared. So r squared equals 4. Which means that r equals 2. So this outer edge, where the plane intersects the cylinder, is going to be at a radius 2 from the z-axis. So when we set up our bounds for this parameterization, we will let r go from 0 to 2. R equals 0 corresponds to points on the z-axis. And I'm going to be taking r all the way out to the outer edge, r equals 2. And since I go all the way around the z-axis, theta is going to go from 0 to 2 pi. So later on, when we do integrals, our integral will be with respect to r and theta, so I'll have a dr d theta. And my bounds will be r goes from 0 to 2, theta goes from 0 to 2 pi. Now this is definitely going to be the better of the 2 ways to parameterize this. But still, let's go back and see what the parameterization would look like if we used spherical coordinates instead. So tell you what, let me save a little bit of time by saying that this is my thought bubble right here. So I'm remembering what spherical coordinates look like, and I'm parameterizing the plane. So I'm going to take the spherical coordinates and substitute in here. So I'm going to replace the z with rho cosine phi. So in spherical coordinates, the equation for that plane is rho cosine phi equals 4. Or if I divide both sides by cosine, I get that rho is 4 secant phi. I can then take that equation for the plane and substitute it back into those equations to eliminate rho. If I do that, I get x equals 4 secant phi times sine phi times cosine theta. Y equals 4 secant phi times sine theta, and z equals 4 secant phi times cosine phi. Simplifying a little bit, secant is 1 over cosine, so secant phi times sine phi is the same as tangent phi. So this is 4 tangent phi cosine theta. Once again, secant phi times sine phi is tangent phi. So y is 4 tangent phi sine theta. This is kind of cute. Secant times cosine is 1. So I get z equals 4, which shouldn't surprise us because our plane is z equals 4. So our parameterization then has parameters phi and theta. And the parameterization is 4 tangent phi cosine theta, 4 tangent phi sine theta, and z equals 4. So not as pretty as what they were when we adapted cylindrical coordinates. Now let's look at what the bounds are going to be. So what bounds on phi and theta are going to describe just that disk? I do need to make a note that the plane is rho equals 4 secant phi. So I'll just make that note down here. Okay, so I only want the portion of the plane which lies inside the cylinder. So let's find what the equation for the cylinder looks like in spherical coordinates. So our bounding cylinder is x squared plus y squared equals 4. Substituting spherical coordinates in, I have rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals 4. We've seen this a few times now, but cosine squared theta plus sine squared theta is 1. So we get rho squared sine squared phi equals 4. So rho sine phi equals 2. And this is the bounding cylinder. So if I want to find out where the cylinder intersects the plane, so if I want to find out where this blue circle is, I need to intersect these two surfaces. I need to intersect rho sine phi equals 2 with rho equals 4 secant phi. So I'm going to take the equation for the plane and substitute it into the equation for the cylinder. That will give me 4 secant phi times sine phi equals 2. Secant phi times sine phi is tangent of phi. And if I divide both sides by 4, I get tangent phi equals 1/2. So the two surfaces intersect when phi is equal to the inverse tangent of 1/2. So let me circle that for a moment. Let's take a side view of this disk. So this horizontal line represents the xy plane. This is the z-axis. And 4 units above the z-axis, here's that blue disk. So notice that I'm looking at it from the side, so all I see is a line segment. What this is telling us is that this bounding circle right here, this edge circle, makes an angle of phi equals the arctangent of 1/2. So if I want to start out on the z-axis and then lean outwards until I get to the edge of the disk, then that's going to correspond with starting at phi equals 0 and continuing outwards until I get to phi equals arctangent of 1/2. So my bounds on phi, if I were to set up an integral, would be phi starts at 0 and stops at arctangent 1/2. Now remember, theta measures the same thing in spherical coordinates as it does in cylindrical coordinates. It measures this angle around the z-axis. So since I want to sweep out the entire disk, I'll let theta go from 0 to 2 pi. So this would be my parameterization, and these would be my bounds on phi and theta.